Hello everyone and welcome back to week 3. In this week we'll actually start playing with some open weights LLMs and we will run them on some data sets. We will try them out and we will fine-tune them and we'll see how each of the things that we apply will affect the model performance. So we'll start this lesson by examining the Llama 3.2 1 billion model, and we will run it over some data set under different conditions. And we will see how these things affect the LLM. So in this lesson, we will not be doing, in this video, sorry, we will not be doing actual fine-tuning yet, but we will run the LLM over some data set. So let's start by introducing the data set that we will use. It's called GSM8K. It's a data set, a very popular one by OpenAI, and it's a math problems data set. So each sample looks like a very basic counting problem. So here's the question, here's the answer. The answer to all of the questions would be some explanation or reasoning, followed by 4 hashes and a number at the very end. So this means that each sample has a correct answer. So you can see whether the model got the final answer correctly or not. And this design of the dataset makes it possible or easily to calculate accuracy, because if you don't have this number, then what it means is you have to evaluate the text itself, and it gets tricky whenever you're trying to evaluate reasoning or text. But now all of these samples have numeric answers, so we can easily compute accuracies. So while this design of the dataset makes it easy to calculate accuracies, you should also know that it is a very harsh way of judging the LLMs, because they don't get partial credit. Like if the answer contains, for example, 3 reasoning steps, the LLM got the first 2 correct, but then it made a mistake on the last one, and hence the final answer was wrong. It means that this sample is incorrect. It's not going to get like half a point or something. It's just an incorrect sample. So this actually means that it's going to be hard fine-tuning the LLMs and trying to bring the accuracy number up. Because yeah, you have to make sure that this number gets correct, and sometimes the LLM might not do the reasoning steps very accurately, but somehow it gets this number correct, and it's going to be evaluated as a correct answer. So just keep that in mind. It's a very harsh way of judging, but we will do it because it makes it easy to calculate accuracies. So we will start this week by having 4 different scenarios that we want to run. So in this notebook, we will be using the Llama 1B, and we want to try different things. We will not be doing fine-tuning yet. We want to run the base model, or the instruction fine-tuned model. We want to run it and see how well it performs on this data set. So we'll run it 4 different times. The first time it's going to be the baseline, meaning we are not doing anything to the model. We're not applying any quantization or adding any adapters or anything. We just take the model, run it on the dataset, and see how it performs. And then we will take the same model, and then we will add adapters to it. We will add the LoRA layers, but we will not be training it. We will just add some layers, the initialization layers, and then we'll run it and see if the performance actually changes. Then we'll do a quantization. We'll quantize the model to be in 4-bit precision, and then we'll run it again. So this one is quantization, but no adapters. And then we will do the last scenario, which is quantized model with LoRA adapters, and we'll see how the performance is. So we will start by preparing our data. So we will load the GSM8K dataset from Hugging Face. And yeah, if you notice, this dataset actually has 2 splits. The training split is 7,400 approximately rows, and then there is the test set. So throughout this program, we will be using the full training set, and this dataset doesn't come with a validation split. So we will create our own validation split, and then we will use it throughout the program. So we're going to have train, validation, and test. We train on the train set. We do any kind of hyperparameter tuning and validate ourselves on the validation set, and then we will be evaluating ourselves on the test set at the very end, when we are done actually implementing all of our models and doing all the fine-tunings. So we'll not be looking at the accuracy on the test set in this lesson. So yeah, we're taking the full training set. From the test set, we are splitting it into test and validation. I think it's 1,000 rows, yeah, 1,300 approximately. We'll be limiting ourselves to 250 samples just because it takes so much time to run these evaluations, and you'll see this when you try it yourself. So after you run this code, you'll be having this validation data object. You can take a look at it quickly. So it's a data set that contains 250 rows, which means you can access the first one, for example, which is a dictionary, contains the question and the answer, and then we have this text field, which is the question, and then the answer marker, and then you stop there. There is nothing else after that, which means this is the prompt that you'll be giving to the LLM, and then the LLM should generate the answer, and then you compare the answer with the truth one. Okay, now we load the model. So here's the Llama 1B. We load the tokenizer, we set the padding token, then we set the padding side. So normally, padding side should be set to left whenever you are generating answers. And in most of the cases, it should be right whenever you're training the model. Okay, so in this case, we are not doing any training yet. So we will pad to the left. And yeah, here we are having some helper methods that helps us evaluate the model. You can take a look at it. It's not hard actually, but basically the idea is that you have a method that extracts the last number from a string. So you give this a string, and if this string has a number or has multiple numbers, it's going to extract the last one. And then what we're doing here is we will be comparing different like the answer, the generation of the model with the truth answer. We extract the numbers at the end, and if they are the same, it means this is correct, otherwise it's not. And then we calculate the accuracy based on this, and we return back the accuracy. Okay, so we will define a LoRA configuration. We said we will do multiple scenarios. One of these scenarios is actually a LoRA scenario. So here's the configuration. We'll do a rank of 8. LoRA alpha, as a rule of thumb, should be 2 times the rank. And then we are targeting these layers. So we're making it simple. I think this is one of the simplest configurations that you can have. And for quantization, we'll be working with 4-bit. We will do the in a 4 variant. We will do double quantization, and then we'll use the BF16 data type. So let's take a look at scenario 1. So this is the baseline, meaning we just loaded the model from Hugging Face. We didn't do anything else. So no LoRA, no quantization. And then we want to evaluate this model on the validation set. So we call the evaluate model method that we defined above. And you can see it starts running on the 250 samples. And the final accuracy is 45%, which is a decent number. This is not actually bad, especially that, as I said, this is either a correct or incorrect answer. Sometimes the model makes very reasonable reasoning steps, but they end up getting a wrong result at the end, so it's considered incorrect. So this is a very high number, actually. So yeah, this is the first scenario. So let's see what happens if you run the same model, but you add LoRA layers and you don't train it, you don't fine-tune it. Turns out it's going to be the same result. And the reason why this is happening is because of the initialization of LoRA layers. So as we know from week 2, LoRA introduces 2 matrices per target matrix, the LoRA A and the LoRA B. In this implementation, when I checked, the LoRA B matrix is always initialized to zeros, which means it doesn't have any effect. So it's not like the LoRA A is randomly initialized, but the LoRA B is 0. And when you multiply them together, you just get 0. And if you add that to the original weight of the model, it doesn't change anything. So it remains the same. So adding LoRA layers with no fine-tuning doesn't actually change the performance at all. The third scenario that we have is quantization. So we will quantize our model into 4-bit 4-bit quantization. We'll use 4-bit quantization. We will do double quantization, but we will not be applying any LoRA layers. So this is just bringing down the size of the model, and you can see the accuracy suddenly drops to 27% without any fine-tuning. So this is just a confirmation that quantization will bring down the performance even if you haven't done any fine-tuning. So just keep this in mind. And then fourth scenario, quantization plus LoRA but untrained. So we haven't done any fine-tuning yet. And as you expect, it's going to be the same number, 27%. This is because quantization brings the performance down, and untrained LoRA does not have any effect because the matrices, one of the matrices is initialized with 0. So I hope this was insightful for you. Whenever you're working with fine-tuning, you will be applying different things. So you might apply LoRA without quantization, you might do quantization only, you might do both of the things, and whenever you're comparing yourself with the baseline, sometimes you'll find that the performance improves, sometimes it gets worse, and you won't be sure what the problem is. So that's why we have this lesson here. We want to show you that sometimes doing some things will not affect the model in any way. Sometimes doing quantization would bring it down just before you perform any fine-tuning. And maybe this reduction with fine-tuning, maybe it after fine-tuning gets better than the baseline, maybe it doesn't. So you got to understand these things just to make sure if you are doing something wrong, maybe you have a bug, or if this is actually expected. So that's it for this video. I hope you found that useful, and I'll see you in the next one.